Okay, first of all, I appreciate you guys being here. It is gorgeous outside, so thank you. I hope I can make this really useful for you. Let's see, I got a couple questions already in the chat, but as this goes, if you could just, type whatever your questions are in the chat, especially if you have a question about, like when I'm in the middle of a question, if there's something you need further clarified, make sure you get that in the chat. Okay, first, let's do a little sound check. Can everybody hear me okay? That's your cue to just type in yes. Okay, thank you. I see that. Good. Okay, so some general stuff about the quiz for tomorrow is it's 8 multiple choice, and then it's a short answer. Okay, so it should take you pretty much, like the full hour, but it is a shorter test. Okay, and you know what? Honestly, it's really just a quiz. It just, I think this chapter is pretty dense, covers a lot of content. Okay, so first question. So I'm going to start with going over some things on the shocking content. As I told you guys, I really think, if you work through the multiple choice on the shocking content page, maybe 21 to 25 or something, really good practice. So it looks like the first one is number 17, and it's a good one. So let me make sure that I'm recording. Yes, I am. I'll let one more person in. All right, so I'm going to go to my whiteboard here. The dog has been found, by the way. Whew, I was nervous about that. Okay, so we are on number 17 on the shocking content. So I guess that's probably about page 22. Okay, this is a great question. So this is number 17. It is a Le Chatelier's principle, but it's got another little component to it, which I like it so well. So I'm just going to rewrite the reaction. Okay, so we got nickel solid, copper 2+. The nickel's being oxidized, and the copper 2+ is being reduced. Okay, and it basically says if the initial concentration of nickel ions is increased. Okay, so I'm going to change colors here. So that means this guy goes up, while the initial concentration of copper 2+ ions remains constant. What will the effect be on Q and the cell potential? Okay, so Q and E cell. Okay, the first thing I wanted to remind you of is when it comes to Q is always like your snapshot. It's always like, okay, these are my conditions, okay? And then Q tells you what's going to happen next. And then E cell is for the aftermath. It's like, okay, the system's going to re-reach equilibrium. Okay, what's that going to cause? Okay, so with that in mind, I'm going to think about Q first. So Q is going to be products over reactants. So that's going to be my nickel 2+ over my copper 2+. And take home message, if you have additional nickel 2+, this is higher. So I think you guys can probably guess that Q is going to be greater. We'll let someone in. There we go. Whoops, let me get rid of that. I talk to myself an awful lot. I know when I'm doing this. Go away. I have a little screen in the middle of my screen. You guys probably can't see it, but it won't go away. All right, we'll just kind of ignore it. Okay, so bottom line, with the addition of nickel 2+, which is a product, that means Q compared to standard conditions meaning that the nickel and the copper 2+ will both be 1 molar and 1 molar, all of a sudden Q is greater, okay? So that answers number 1, Q is larger. So then because of that, compared to a standard cell, this guy is gonna shift backwards, okay? Hold on, there we go. So you got too much product, so to get rid of that, you're gonna shift backwards. But when I say shift backwards, it's still a galvanic cell. So in my class, I like to say it's shifting less forward, okay? So E cell is gonna go down, but it's still gonna be positive. So what that means for our choices is that's why C is the correct answer. Q will increase. That's because of the addition of nickel 2+. That's my stress. And then as a result, the reaction is going to shift backwards compared to a standard cell. In other words, E is going to be less positive than it would normally be. Okay, so I hope that answers that question. It's a tricky one. It's a really good one. While we're on this page, number 17 is a good one. Number 19 is a really good one as well, and 20. Okay, so if you have any questions about 19 or 20, please make sure you ask. Okay, so I think that takes care of that one. So I'm going to move on to, and I'm looking at the chat to see if there's any additional questions about that. Okay, it's looking good. So let's see. I'm going to skip to question 13 on the shocking content. Ooh, another really good one. Okay, so this is number 13. I have no idea what page that is, but hopefully you guys can find that. I guess I could look it up real quick. It looks like it's number 13 on page 23. Okay, page 23. Okay, so this one. All right, so it says, based on the reduction potentials given above, which of the following would be expected to occur when electrodes connected to the terminals of a 2-volt battery are immersed in a solution of sodium chloride and water? Okay. All right, so a couple really important clues in that problem. First of all, it says electrodes are connected to terminals of a 2-volt battery. So that, first of all, implies that this is an electrolytic cell. Okay, so this is electrolytic. Whoops, sorry about the crazy handwriting, which means that E cell, okay, is going to be negative for this. Okay, and while we're talking about it, since it's electrolytic, E cell will be negative, delta G will be positive, K will be less than 1. So you can sort of just assume all of that just from the fact that it's electrolytic, right? Because it's hooked up to a battery source. We're forcing an unfavorable reaction to happen, okay? Now, it's a sodium chloride solution. So basically, the only things available to us are Na+, Cl-, and water, okay? Those are the only species, if you will, that are available in that solution. So then it says, which of the statements are true? Well, if you guys look at the half reactions that are provided, I think the catch is that what I want you to notice is that on number 13, and for heaven's sakes, if you need to go get it off your desk or something like that, I would definitely do that. Okay, so you can see what I'm talking about. But for number 13, you know, all the half reactions, there's 3 of them listed, they're all written as reductions. Okay, so they're written as if they're coming off your white sheet. They're coming off your standard reduction potentials table. Okay, but that doesn't necessarily mean that all those half reactions are possible the way they're written. So looking at the first one, number 13, it's basically water, and I'm just going to abbreviate it a little bit. Okay, so I don't have all the coefficients and stuff, and that's okay. Okay, the water is being reduced. So water can be reduced because water is present, so that's fine. The next one is Na+, okay, being reduced. Okay, and guess what? That one's fine too, because Na+ is available in the solution. But it's that last half reaction. It says Cl2 plus 2 electrons, making Cl-. Well, guess what? That reaction can't happen the way it's written, okay? Because there is no Cl2 available in my original setup. It's just not there, okay? But what I do have is Cl-, okay? So what that's telling me is that as written, this reaction really isn't really a possibility. But what can happen is that this can be my oxidation. So I can take the 2 Cl- ions that are available in that solution, and I could look into this oxidation, okay? But of course, as soon as I do that, whatever that E value is, I'm gonna have to remember to switch the sign because I flipped it. So I think that's the challenging part of this particular question, is that these are the half reactions that are possible. The top 2 are, the top 2 are reductions, and then the Cl- one is your only oxidation. Now I think I can answer the question. So just like in the electrolysis mini lab that you did in class, and like what was on the quiz on Friday, you have to pick the absolute most favorable reduction and the absolute most favorable oxidation. So we're going to do exactly that. So what that means is between these two, got 2 choices for the reduction. Okay, if I look at the potentials, I got -0.8 and -2.7. You want to pick the least negative, most positive value. So you know what? I'm going to go ahead and pick the -0.81. Okay, so this is my more favorable reduction. This guy is not going to happen. Okay, so I got my reduction. Okay, and then for my oxidation, I really only had that one choice. Okay, and that was this guy right here. Okay, so I think what was challenging about that problem is you really have to pay attention to how the information is presented to you. In this case, you had a list of reductions, so you had to know that based on what materials were available in the solution at the start of the experiment, what half reactions were possible. Okay, so you had to know that you needed to flip that chlorine reaction to make it 2 Cl- being oxidized. Okay, so now that I have that, I think what really throws students off about that question though, and it kind of bothers me too, is negative 1.4 and a negative 0.8. That actually adds up to what 2.2, negative 2.2 volts, which that's fine. But in the actual prompt, it says that it was hooked up to a 2.0 volt battery. So kind of in my assessment, that's a bit of a typo. To be honest, really, this reaction wouldn't be able to happen at all because you have to provide at least this voltage, okay, to overcome and make this unfavorable process happen. You know what I mean? So that's always kind of bothered me. We pulled these questions out of a pretty reputable source. So, but I really should change that. Okay, the voltage, the battery source that's being provided should be like at least 2.2 volts or greater. Okay, so that's one thing. Maybe that's what threw some of you guys off. Now, in terms of the choices, let's go over the right one first, because it says chlorine gas will appear at the anode. Okay, so do remember, keep your vowels together. So the oxidation will take place at the anode. Okay, and reduction will take place at the cathode. So chlorine gas will appear at the anode. Okay, and that is absolutely true because I see it being produced there. And hydrogen gas will appear at the cathode. So here's where reduction is, and I am generating hydrogen gas. So I think E is the best answer. If you look at some of the other choices, they just don't match up right. Okay, something's not right about the anode or the cathode or which reactions were picked. Okay, so I hope that one helps. It was a really great question, very similar to what was seen on the quiz on Friday. And yes, there's a question just like this that you're going to see tomorrow as well. Okay, so if that's all right, I'm going to be done with number 13, but I'm going to look in the chat to see if I see any concerns about this particular one. Okay, so I'm looking at the bottom of the chat to see if you guys have any additional questions about this one, or just yell it out for heaven's sakes. That would be totally fine with me. Okay, so that would be number 13. While we're on that page, I really like number 16 as well. So, and I kind of already answered it at the beginning of this one, but maybe put a star by number 16, very important question. Okay, so let's go back and see what else we have. Let's see, so I'm gonna see if there's any other questions from shocking content. And don't hesitate, just type them in when you get to it. 2A on page 25. Okay, all right, so it looks like the questions I see now are about the short answers, so I'll jump to that. Let's see, part A on page 20. Okay, so let's see, whoever asked about page 20, we never did cover that in class. It was about basically how a lead storage battery works, basically like your car battery works. And I would just honestly say, don't worry about it, okay? I could give you something similar to it in a minute, but I would say just don't worry about that one, okay? So that being said, about page 25, question 2. Okay, ooh, I like, yes, these are some good ones here. So I'll give you guys some hints about, ooh, I'm not sure I like that yellow. Whoa, now I'm not writing. Still not writing. Let's see, how about page 25, short answer question number 2. Okay, so ooh, this is a good one. I do like this one. Okay, so it says, and again, hopefully you have your binder packet with you so you can read the question with me. It says an 800 milliliter sample of 0.080 molar Ag plus solution was electrolyzed. Ooh, already it says electrolyzed. Okay, and electrolyzed is basically a synonym for an electrolytic cell. So we must be, this is a not favorable reaction. Okay, we must be hooking it up to a battery supply, resulting in the formation of solid silver and oxygen gas. Okay, so that's some real important hints about what the half reactions are that are occurring here. The solution was subjected to a current of 2 amps. I'm teaching gas laws in regular chem for 10 minutes. Okay. The solution becomes progressively more acidic. Ooh, that's another important hint. Okay, so H plus goes up as the reaction progresses. Okay, so I think the key to this one is if you can do A, you can probably do all the rest of the parts. So write the 2 half reactions that occur, stating which takes place at the anode and which takes place at the cathode. Okay, so I'm going to start at the cathode. Okay, So the cathode is where reduction is taking place, okay? And I know we started with an Ag plus solution, okay, like silver nitrate or something like that. So, and we ended with silver metal. So that to me sounds like it's going to be our reduction. So Ag plus must be gaining 1 electron and making Ag solid, okay? So that's consistent with what I started with in the problem, and then it's consistent with what it told me for the products. Okay. All right, so that would be my cathode. Okay, now at the anode, this might be what kind of threw you off a little bit. It's like, oh goodness, where's this oxygen coming from? Okay, and where's this, how's it becoming more acidic? So I hope that from the lab that we did, the electrolysis mini lab, you would recognize, ooh, you know what, water might be involved here. So I think everything points to somehow water is part of the oxidation. Okay, so if you look at your white sheet, okay, and I could switch to that right now, but that would be like a whole confusing mess, and I'd have to stop sharing and then reshare and then look at it and then come back. So if you don't mind, I'm not going to look at the white sheet, but hopefully you are. When I say the white sheet, you know what I mean, right? Okay, the standard reduction potentials. I don't know if you guys can still see me on the screen, but pointing to what document I'm looking at. So you're looking at the white sheet, right? Okay, and I'm looking at the white sheet and I'm going to find water being oxidized. So that means I'm on the right-hand side. Okay, and I'm going to look, maybe about 2/3 down. Okay, and I'm looking for water being oxidized. Okay, which is, actually, I lied. Where is water being oxidized? Sorry, I know I'm looking at it. I see H2O2. Ah, thank you. Whew. So it's about maybe the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10th one from the top on the right. Okay, so basically this is what the half reaction is. Okay, 2 water. You remember I'm looking at the white sheet, but I'm looking for the oxidation. So I'm looking at the reaction backwards, making O2 plus 4H plus, and then plus 4 electrons. Okay, so hopefully you guys are able to find that on the white sheet. And that, I guess, for sure is what the reaction would be going on at the anode. It's oxidation. Okay, and how do I know that? Because I know water's there, and it tells me that oxygen was created. So I had to come up with some kind of oxidation that produces water. Now, if you're like, gosh, how would I do that on the test? The good thing about the test is when you need a half reaction, it's given in the problem. So you don't have to sit there and scroll through the white sheet and spend half the test trying to find the right half reaction. Okay, so in that sense, I think the test is going to be a lot easier than some of your practice. Okay, take home message. It looks like we have a reaction at the cathode, we have a reaction at the anode, and that takes care of letter A. Now the problem gets even funner. It says if oxygen gas was produced in the electrolysis and it was collected at standard temperature and pressure, what would be its volume? Okay, so with that in mind, this time, this is really important. We're going back to that process where if I give you time, okay, you should be able to figure out how much stuff you could collect, okay? Vice versa, if I give you stuff that you collected, you should be able to go backwards and see how long it takes. So in this case, it says, gosh, what would be the volume of oxygen collected? So that's like amount of stuff. So I'm going to start with the time. Okay, and for this experiment, it started with 10 minutes. Okay, so you either start with time or you start with the amount of stuff. Okay, I can't do anything with minutes, so I'm going to go ahead and convert the minutes to seconds. Okay, and now we get into some of those conversions that I hope you guys are really, really, really well practiced with. Okay, so I'm going to put seconds down here. Okay, how can I go from seconds to somehow talking about how much charge would that be in total? Okay, and that's where the amps come in. Okay, so this would be the current. Okay, so I'm going to go back and read the problem, and it said that the experiment was run at 2 amps, 2 amperes. Okay, so the definition of an ampere is how many coulombs for every 1 second. Okay, so how is that looking? Okay, so the seconds cancel out, the minutes cancel out. So right now I would know how much charge passes through during that duration of the experiment. Okay, but now I want to take that charge and see, oh goodness, well, if that much charge passed through, how many electrons is that anyway? Okay, or in other words, moles of electrons. So this is where Faraday's constant comes in. Okay, Faradays. Okay, and don't worry, this is given on your green sheet, so you should make sure that you can find it, but 96,500. And honestly, I think in your green sheet, they might say 96,465 or something like that. I don't care what number you use, something close to 96,500, okay? My memory is not that great, so that's the number I have in my head, and I'm just gonna keep it that way. Okay, and then I think probably this next step is the most easily forgotten and maybe the most difficult. Okay, so we want to go from moles of electrons to whatever substance we're collecting. So in this case, we were interested in oxygen. Okay, so now I go back to this half reaction and I say, oh, okay, well, it looks like 4 moles of electrons produce 1 mole of oxygen. Okay, so I'm going to go ahead and fill that in. 4 moles of electrons, 1 mole of oxygen. Okay, so if you did all that right, you will come up with a number. I think it comes out to maybe like 0.0031. How does that sound? Okay, and then you guys from here, guess what? If you were thinking gas laws, you're absolutely right. So you guys are going to use Pivnert. I think you're probably good to go from here. You're looking for the volume. You have the moles. You have R, 0.0821 if you forgot. I think the temp, what did it say? I think it said at standard temperature and pressure. Okay, so you have the temp and you have the pressure. In fact, since we're at standard temperature and pressure, I didn't catch that. We can actually do that one step easier. Whoops, let me fix that. I put moles of electrons, but that really should be moles of O2. Whoops, let me try that again. Moles of O2. So watch this. If you guys remember, since we're at SDP, for every 1 mole of O2, it's going to take up 22.4 liters. Okay, so you're welcome to use that conversion factor as well if you remember it. Okay, so that's how B comes into play. All right, so somebody asked about question 2, part B. Okay, and I'm guessing, and that was 2A, so I think I did both those. But while I'm at it, I think actually the hardest part of this question was 2C, and I'll just tell you why. It says, what would be the mass of solid silver produced in this electrolysis? The key is you got to know what number to start with. Okay, so now we're talking about the mass of silver. So, you know, you could have started in the original problem. It said that you had a 0.08, I think it was 0.08 molar solution. You could have started with this. Okay, but I'm going to tell you that's the wrong thing to do because that's an excess. Okay, you have way more of that than you need. Okay. So what you really need to start with is think of this as a limiting reactant problem, that if you know you're going to generate that much O2, that's kind of like your limiting reactant, then you can use that to see how much silver you could plate. Okay, so just to give you a little FYI on that. So for letter C, using the amount of O2 that you know you generated, then you can go from moles of oxygen to moles of silver. Okay, and you have to be careful with that step too, because what's the ratio? I'm going to go back for a second here. Give me a second to figure out how to go back. You might say, oh yeah, O2 and silver, they're in a 1-to-1 ratio, but that's actually not true because there's 4 electrons here. So we didn't go through the process, but if you actually added those half reactions up, you'd have to make sure that those electrons cancel out. So if you have 4 electrons here, you'd have to have 4 electrons here. So guess what you'd have to multiply this half reaction by? You'd have to multiply it by 4. Okay, so if it didn't occur to you to do that, okay, you'd find that your answer is going to be like a fourth of what it should be. Okay, so for every 1 mole of oxygen, you're going to generate 4 moles of silver. So that's kind of the tricky part there. And then of course you can just convert it to mass. I think molar mass is around 107. Okay. So there you have it. And actually by doing letter C, yep, that was letter C. And then for letter D, boy, oh boy, I'm gonna tell you, you don't have to worry about it for the test tomorrow, but it's kind of a flashback from the past. You actually had to do a little pH calculation. But long story short, letter D is pretty easy. As long as you just go, you calculate the H plus that would be from this amount of O2. So you just go from O2 to H plus, and then just take the negative log of that, right? Because that'd be your pH, okay? So I'll just leave it at that. If you can get to C, then I'm sure you'll be able to do D as well. All right, so looking at the chat to make sure were there any further questions about number 2 in its glory? A, B, C, or D? Let's see. I see someone asking about number 5, and I see someone asking about number 4. So any other questions about number 2? Give you guys a second if you want to jump it or just type it in the chat or just yell it out. Okay, so I guess we're looking pretty good there. So let's see the next one. It looks like number 4. All right, this one has some really good components to it as well. So number 4, it seems really simple. Okay, you just have this nice, like deceptively, I would say, simple galvanic cell. Okay, looks something like this. Okay, and I think the question someone was asking about C. So it looks like I'm guessing that 4A was probably pretty easy. 4B was probably easy. No one asked about those, so I'm just going to let it go because really letter C is the important one. So again, this is number 4, page 26. Okay, and here's our galvanic cell, and people are asking about letter C. And the cool thing about it is this would be true for any galvanic cell. Okay, so you could apply it in a lot of different questions. It says, describe the changes that occur in the quantities below as the reaction proceeds in the forward direction. Okay, so let me just make that a little more legible. Okay, I'm trying here, people. Okay, so again, this is letter C. Okay, so first one, letter I is talking about the MX plus. So as this reaction proceeds, okay, and I'm just going to get rid of this line here. There we go. As the reaction proceeds, so I want you guys to think about it. So let's just say you start with, a standard cell, 1 molar, 1 molar, okay? As this reaction proceeds, it's going to go obviously in the forward direction, okay? But as soon as you go in the forward direction, all of a sudden, the amount of M plus is going to increase and the amount of cadmium 2 plus is going to decrease. Okay, so those numbers are going to change. The 1 molar on this side is going to go down to like 0.9, 0.8, 0.7, and so on. And the M plus is going to go up, 1.1, 1.2, and so on. Do you guys see what I'm saying? That's how reactions happen, right? You make products and you get rid of reactants, okay? So what would happen to the M plus? Well, it would just keep increasing. Okay, it would keep increasing until equilibrium is reached. Okay, that sounds good. Now for the next one, this is where it gets interesting. So now II, what about E cell? Okay, so E cell, of course, in your standard, when you first start, it's going to be at its absolute most positive value. But as the reaction proceeds and as your product goes up, like we talked about, and your reactant goes up, that as your reactant goes down, that's going to drive the reaction to go backwards. But I say backwards loosely because really what I mean is that the reaction will be driven less in the forward direction. You guys know what I mean? So I can't remember for this one. I guess I probably do know that. I'm not sure if I knew the answer or not, but let's just say like E cell started at 1.7. Okay, and I'm just making up a number. I know that that's probably not what it is. Doesn't matter. Let's say E cell is 1.7, and that's for a standard cell. Okay, so as M plus goes up and CD2 plus goes down, as the reaction proceeds, it's going to go less. It's going to be driven less in the forward direction. So then next thing you know, it'd be 1.6 volts, it'd be 1.4 volts, it'd be 1.2 volts, and so on. 0.8 volts, and so on and so forth, until it goes down to 0. Okay, and that's the key because once you reach 0, the reaction is at equilibrium. Okay, so the way I would answer that is I would say, oh, as this battery proceeds, it's going to be driven less and less in the forward direction. So E cell is going to become less and less positive until eventually the battery dies and E cell is 0. The system is at equilibrium. Okay, there's no more driving force to move electrons if the reaction's at equilibrium. Okay. And then honestly, it's the same thing about G. Now, one thing that might bother you, it bothered me, is they're using G. And I think really the only way this question makes sense is they're actually talking about delta G. Okay, so fix that. So delta G, of course, this was a galvanic cell. So delta G is negative, but as the reaction proceeds in the forward direction, right? It's going to be driven less and less in the forward direction. So it's going to become a less and less negative number until, guess what? Delta G equals 0. And then the process, the battery, the reaction is at equilibrium. Okay, so really, really, really great question. I'm not sure who asked that, but I'm really glad that you asked that. And the bottom line is, doesn't matter what the galvanic cell is, you know, whatever the standard conditions are, that's when E cell is going to be its most positive. And then as the battery reaction continues and continues and continues, E cell is going to become less and less and less positive until boom, okay, the battery dies. And that means that E cell is 0, delta G is 0, the system, the battery is at equilibrium. Okay. So again, I'm going to look in the chat and see if anybody has more clarification questions on that one. Yep. So Kavya, just, I see it was your question, and just to clarify, it says, how come E cell goes down even though the reaction proceeds in the forward direction? So that's why I really like to say it this way, that the reaction, it doesn't really shift backwards. It's just, it's being driven, it's driven less in the forward direction. So that's what it means when E cell goes down, becomes less and less positive. But as long as it's positive, it is still favorable in the forward direction. Okay. Never, a galvanic cell can't have a negative E cell unless it's been converted into an electrolytic, which means you hooked it up to a battery. Okay. So hopefully, Kavya or anybody else, if I can give you further clarification on that, let me know. Okay, so I'm thinking that's pretty good with number 4, but I'm looking to see if anyone wanted to add something to the chat. Okay, Aruba asked, great question. She said, when would E cell increase? Okay, I can definitely answer that one. So I'm going to use the same reaction here. I'm going to get rid of some of this stuff if you don't mind. So what are some other shifts that we can do? Let me show you. Oops, slowly but surely, this erase function is kind of slow. Okay, so what would be an example of how E cell could become larger? Okay, so I'm going to clean this up a little bit if you don't mind. Okay, oops, I might as well just use a different screen, huh? Okay, so I'm going to rewrite cadmium 2+, and then here's my M. I do this right? Yep, so cadmium got reduced and M got oxidized. Okay, good. So you know what? Let's just say this is E0, which means that would be assuming that this is 1 molar. Everything's 1 molar. So 1 molar and 1 molar. So what's something that would cause it to go in the forward direction? How about some, this is kind of creative, some sodium phosphate solution. Nope, sorry. Let me clarify that. Some sodium phosphate solid was added to the reduction side, to the cathode side. Okay, so first of all, I said the cathode side. So what that means is you got to look at what's being reduced. Okay, and that would be the cadmium 2+ side. Okay, and you say to yourself, sodium phosphate, what the heck is that going to do? Well, what you might want to remember is that anytime you had any ionic compound that has an alkali metal in it, same thing with nitrates, it is totally a strong electrolyte. So as soon as sodium phosphate hits that cadmium 2+ solution, okay, that we would assume, you know, if you guys think about this type of battery, you'd have cadmium 2+, right? And this would be your cadmium metal. They'd be connected, okay, to the M and all that good stuff. But if I added some sodium phosphate, it would immediately dissociate. So in other words, I'd be adding Na+ ions, and I'd be adding phosphate ions, okay? Well, you know, I don't know if you remember, but cadmium phosphate, that is a precipitate. Okay, so guess what? This would make a solid at the bottom, and effectively you're lowering your cadmium 2+ concentration. Okay, and you know what? I just did that wrong, meaning if the cadmium 2+ lowered, then it would shift backwards as well, meaning less forward. So that's another thing that would cause E cell to go down. So I'm sorry, what I really would have said is something was added to the M2+ side. Okay, that's what we need to reduce. Okay, so how about maybe, oh, yes, maybe M2 plus makes a precipitate with chloride ions. Okay, like maybe, you know, and by the way, it's just, you know what, I might have messed that up too, and I apologize. Doesn't really make a difference at all, but it's M plus, okay? So what if maybe like M plus is something like silver ions, okay? So it's M plus, makes it precipitate with Cl minus like Ag plus would, okay? So then you would make this solid, and that would be a way of lowering the M plus, okay? And that would shift the reaction forward. So instead of E cell of 1.7, it might be 1.8, might be 1.9. Okay, so Le Chatelier's principle says that if you remove a product, that would cause the equilibrium to shift forward. Okay, so while we're at it, I'm kind of going off of what you guys were asking about number 16 a minute ago. So I'm just gonna get rid of this guy. Okay, if we did the part that's in red there, just to review, what you would see there is what would happen to Q. So as soon as you lowered the M plus, okay, by adding Cl minus and making a precipitate, okay, then Q would lower, right? Because would decrease, because all of a sudden you have less of that product, okay? And when Q lowers, okay, how do you get Q back to where it was? You shift forward, okay? So that's another way of saying it. E cell would increase, okay? And while we're at it, since you guys asked, I can think of one more. What if you diluted both solutions? Okay, so you guys have this battery and you got these aqueous solutions on either side of the battery, okay, in the anode side and the cathode side. What if you added, you know, 100 mils of water to both beakers? Okay, and you might say, oh, well, what the heck would water do? But of course, water is going to dilute, okay? It's going to dilute both sides, okay? And so as a result, you're going to shift to the side, with more aqueous particles. Okay, so that would mean it would shift forward. So again, E cell would increase, okay? And you might say, wait a second, doesn't it look like, you know, like there's equal amounts of aqueous particles? Okay, and honestly, I would say that this reaction wasn't balanced because if this is indeed a +1, okay, that means you'd have to put a 2 in front so that 2 electrons were lost to match the 2 electrons being gained here. Okay, so, and that's okay, the reaction wasn't balanced, okay, but you would have to know if it was necessary to balance it. Okay, so it would shift forward because 2 moles of aqueous particles on the product side going to shift towards that side to compensate for the dilution. Okay, so let me see some people added some things that said, would E cell also go up if M plus was higher molarity than CD2 plus? So if that's a great point, okay, but I think it would be the exact opposite. So the question was basically, I'll clean this up a little bit here. Yeah, in terms of, you know, if you deal with these molarities, you would have to have, if this guy was like 2 molar and this guy was 1 molar, then you'd have too much cadmium 2+ compared to a standard solution, and that would shift forward, okay? So I think that's what you're talking about, okay? Guys, bottom line is Le Chatelier's principle works exactly the same with these reactions as it ever has before. So if you increase reactants, you're going to shift to get rid of them, so you're going to shift forward, okay? If you increase products, that means you got too much on the product side, so you're going to shift away from the product side, you're going to shift backwards, okay? So Shalini, hopefully that makes sense. Okay, that if the cadmium was a higher molarity, then it would indeed shift forward, okay? Let's see, I'm looking to see if there's any other questions about this one. I did see, before we leave this page, I did see someone ask about number 5. Okay, and actually a lot of you guys had questions. This one kind of relates to the quiz that you guys took on Friday, because there was a question about the electrolysis of sodium chloride. So this one, molten sodium chloride can be electrolyzed to form pure sodium and chlorine. So just going back to that question. So if you take sodium chloride, okay, but it's molten. So that means it's going to be in liquid form. And the thing about liquids and aqueous media is that in both cases, if it's an electrolyte, they can split up. So another way of writing the same thing would be this, okay? So this and this, that's the same thing, okay? Molten, let me make sure it looks like molten, okay? Because in molten, that means that the ionic compound is liquid, it can dissociate into its ions. So it doesn't matter which one you look at, but bottom line, the important part is that when you electrolyze a molten ionic compound, it will be broken into its elemental forms. So Na plus is going to go to Na solid, and Cl minus is going to go to Cl2 gas. Okay, so those would be the products. The exact same thing if you, like on the quiz, started off this way. So the important part is that sodium was a positive and it went to sodium as a 0. It was reduced. Okay, and Cl minus, it was a minus, and then it went to chlorine gas, which is 0. It got oxidized. Okay, so that's the important part. Okay, is the ionic compound is electrolyzed into its elemental forms, sodium, metal, and chlorine gas. Okay, this exact same thing. It's actually probably better because it's showing that this guy is a strong electrolyte and it broke up. Okay, so that's the first part that caught my eye about number 5. And then let's see, someone just asked me to go over number 5. Let's see. I think basically that is letter A. Okay, so real quickly though, it says to break into its half reactions. So let's see. So this is number 5 on page 26. Okay, so for the anode, oxidation takes place at the anode. That would be your 2 Cl minuses, okay, from here, turning into chlorine gas and gaining 2 electrons. So that's my anode, and my reduction at the cathode would be the Na plus. Whoops, I forgot to gain the electrons. Okay, plus 1 electron equaling. Okay, and whether you put solid or liquid, I don't really care, but it's just, it doesn't have a charge because it went to the metal, but it's probably really hot, so I imagine it'd be in liquid form. Okay, so those are the half reactions. If you had all this doubled, that's fine too, because the next step, if you add these together, would be that you wouldn't need double that. Okay, and then C says for the electrolysis of molten sodium chloride, what were the values? Okay, and this one's probably the important one. So what would E cell be? They call it E of reaction. That's the same thing as E cell. It will be negative because this is electrolysis. So we're hooking it up to a battery source and we're forcing this unfavorable reaction to happen. And then just the same, delta G would be positive because this is thermodynamically unfavorable. But delta S, let's see, so we're taking basically this ionic compound, okay, and we're generating this gas. So what I see is that we're generating a mole of chlorine gas. So it looks like we're increasing in disorder, or we're increasing in how dispersed the matter can be. So I would say that entropy is positive. Okay, so that's a good question. Number 5C. And then D, explain why when the molten sodium chloride is replaced with aqueous solutions of sodium chloride, pure sodium is not produced. That's a great question too, because for letter D, as soon as you make an aqueous solution, that's what water is going to start getting involved. Okay, so believe you me, Na plus does not want to be reduced to sodium. So instead, I promise you, water would be reduced instead to produce hydrogen. Okay, so you would get conflicting reactions if you made it aqueous, and you wouldn't get the one you'd want. You'd get hydrogen gas instead of sodium metal. Okay, so that would be number 5. All right, so let's see. I'm basically thinking that we have gone through just about all the short answers. So if there's any questions on page 25 or 26, see somebody asked about 1C. Okay. Yep, I can talk about that. Any other questions from page 25, 26, page 25, 26? Looking through the chat. All right. Good. So real quickly, I'll go back to somebody asked about number 1. Okay, and this was on page 25. So I think they were asking specifically. So this is a really good question, number 1, and it should have been pretty simple. Okay, all you had to do was, calculate E cell, but B and C really easy, but make sure you practice them. So letter B asked you to calculate delta G. And again, this formula is given, it's on the green sheet, but you might want to familiarize yourself, make sure you know where to find it. Okay, so delta G for that one. N, remember, is moles of electrons transferred. Okay, and then Faraday's constant is 96,500. Okay, and Faraday's constant, the units are usually coulombs per second. Like that's what it says on the green sheet. Okay, but that doesn't really help us in this particular formula because, by the time we get to delta G, we get in joules. Okay, so, if we use these units, coulombs per second, I don't really see joules. So I told my students that really 1 coulomb also equals a joule per volt. Okay, like that's just, if you break it down further, okay, that's just what that is. Okay, so as a result, what we end up with is joule per second per volt. Okay, meaning the seconds was already there because it was coulombs per second, and then a coulomb is a joule per volt. Okay, so you guys see where that's coming from? Okay, and the reason why that's important is then you multiply it by the E cell, which is in volts. Okay, so long story short, the reason why I went through that is because you should be able to show that the volts cancel out with the volts. Okay, and the moles cancel out with the moles. Okay, of electrons. Okay, and joules per second. I messed something up there. Okay, hold on a second. Okay, I'm losing my ever living mind here. Joules per mole, electron per volt. Okay, so the volts cancel out with the volts, and the moles of electrons cancel out the moles of electrons. Sorry. Okay, and you guys, long story short, is you're left with joules. Okay, so make sure that your units for delta G are indeed joules, and keep in mind it's going to be a really big number because then you would typically convert it to kilojoules. Okay, now somebody had asked about letter C. What is the value for K? Okay, and just remember, you guys have another formula for that. Okay, and you guys can look something like this. Again, it's given on your equation sheet. 592 over n log K. Okay, so look it up. Make sure you guys can find it. Make sure that's a little neater. There we go. Okay, so this, if you can go back in the notes, you can look it up, is kind of like a merge of all the standard values that are in this particular problem. So it's just given, N is moles of electrons transferred, and then log K. So now you should be able to solve for K. Okay, you have the voltage from E cell, 592, and then the 2, N is a moles of electrons transferred, which is 2 for this problem. Okay, that's moles. Okay, and then log K. Okay, so you should be able to manipulate that. Just recall, how do you get rid of logs? Okay, you got to do 10 raised to the power. That's how you get rid of that. Okay, 10 raised to the power should allow you to get rid of that log so that you can then solve for K. So give it a try. If you have some problems working the numbers, give me a yell. Okay, in the chat. But those should be kind of like easy questions. So make sure that you guys can work those. Okay. All right. Let's see. So I'm looking to see. That's it for the short answer. How about, I see some other questions on the tracking content. Looks like 18. Okay, we'll take a look at that. Okay, so back to the shocking content. So I think that's pages 21 to 24, I guess, and number 18. It says, oh, this one is kind of a tricky one. It says, when solid copper shavings are placed in a solution of dilute HNO3, copper 2+ appears and NO gas bubbles form. Which of the following has occurred? Okay, so our general reaction is copper shavings from solid are placed in HNO3. Now, if you're not paying attention, you might say to yourself, oh, right, single replacement. And you might think, oh, I'm going to make copper nitrate and then I'm going to make hydrogen gas. But that is not the reaction they're describing. Okay, because notice in the language it says NO bubbles are formed and we're making hydrogen here. Okay, so in fact, if you look at your white sheet, copper does not have enough reducing ability to displace hydrogen out of nitric acid. Okay? Copper is not a reactive enough metal. Okay, so this reaction does not take place. If you looked it up on your white sheet, you get a negative E cell, not happening. Okay, so instead, you had to look a little more closely, and it's basically saying, oh gosh, well, some other reactions taking place. So it implies that you made NO gas. Okay, so, and it said something about copper 2+. So this is still my oxidation, okay, but instead of hydrogen being reduced, it looks like the nitrogen is being reduced instead. Okay, so I think nitrogen is like +5 right here, and it's a +2 right here. So that is showing reduction. Okay, so that's why B is the correct answer. It says copper has been oxidized by nitrate. Okay, so that one's a pretty good one. What else you got? So if there's other questions on the on the shocking content. Okay, and kind of while we're talking about that, there's a question I might like to bring up. Let me see how I want to phrase it. You guys, one of the skills that Ms. Schneider and I really emphasize a lot is just being really, really good at interpreting that silly white sheet, okay? And I did promise you that, guess what? We're not gonna give you like the white sheet at all. In fact, we're gonna pull out just the half reactions you want. So let's just say I'm looking at the white sheet. Since you guys mentioned nitrate, I'm gonna give me a second just to write a couple half reactions up here. I'm taking them straight off the white sheet. Okay, so there's that one we're just talking about with nitrate. Okay, and this is 0.96. Okay, and then I'm gonna give you guys a couple other ones. Okay, unfortunately, this takes just a minute, so picking out some that I like. Let's find another one. Oh yeah, that's a good one. Okay. Copper 2+. Can't do anything without copper 2+. Okay, thanks for waiting. This will be a good question, I promise you. I wouldn't bring it up if it wasn't. And then one more. Okay, and this is kind of how the problem would be presented. Okay, so I took these all off the left side of the white sheet, okay? So this is what my question might read. I might say something like, what species can cause the oxidation of acidified nitrate ions. Hold on 1 second. Reduction. The reduction of acidified nitrate ions, but not acidified sulfate ions. Sorry, it took me a minute to write all this out. Okay, so which species can cause the reduction of acidified nitrate ions, but cannot cause, and I'm going to switch this one more time. You guys are very patient. I'm going to flip those if you guys don't mind. Hold on 1 sec. Okay, can cause the reduction Hold on, give me 1 second. Nitrate can cause oxidation. I think I gotta flip these. Okay. Okay, and I'm gonna give you guys choices. Hold on 1 second. Okay. Let me make sure I got this right. Copper cannot bicarbonate. So you guys notice, even with me writing the questions, these questions can be kind of tricky, okay? Okay, so which species can cause the reduction? That's yes. Okay. Okay, so I'm going to give you guys some choices. Okay, so my choices are, you guys ready? I'm going to change colors one more time. Whoops. Okay, so I'm going to give you AU, AU3+, copper, copper 2+, okay, or that's it. Those are your choices, okay? So again, it says which species can cause the reduction of acidified sulfate, but not acidified nitrate, okay? So what I want you guys to clarify from this, and these are the path reactions will be given to you, okay? So, okay, what does that mean? If it's caught what are we doing with the sulfate and the nitrate? So we're reducing them, okay? So we have this reduction, okay, and it has a potential of 0.96. And we have this reduction. Okay, and it says it can cause reduction of one of them, but not the other. Okay, so what does that mean is happening to the species? Okay, so I'll tell you of these 4 choices. I'm just going to put a box around them. Okay, so that's A, B, C, and D, right? Well, 2 of these are not possible choices, okay? Because if we are dealing with the reduction of sulfate and the reduction of nitrate, those are my reductions. So guess what? I can't have another reduction, okay? So AU3+ is off the table because it's not going to be reduced as well. And copper 2+ is off the table because it's not going to be reduced as well, okay? So we can't have multiple reductions. So basically, my answer has to come down to one of these 2. Okay, and I'm sure that your gut's telling you that it's the one in the middle, and you would be absolutely right. Okay, but why? Okay, so by nitrate being oxidized, or sorry, by nitrate being reduced, it can cause the oxidation of copper. Okay, but by sulfate being reduced, it doesn't have enough potential to cause the oxidation of copper as well. So which species can cause the reduction of? So again, you know what? I got this wrong. I'm sorry. I have to switch those. I had it right the first time. Okay, so I'm gonna change those back. I'm sorry. Okay, and the good news is you guys, you know what? The math can always save you. So if you get like your head gets kind of muddled with these questions, just go to the math. As long as you're really sure what your reduction is and what your oxidation is. So for instance, if you take that sulfate and acidified just means it has to have H+ present, which it does, so that's fine. So if this is my reduction right here, okay, that's negative 1.7. Okay, and if I want my oxidation to be copper, okay, then we'd have to flip it this way. Okay, then I would change the sign to negative 0.34. Okay, and if I put those together, E cell is going to be negative overall. So that reaction is not going to happen. Okay, so copper does not have, by copper being oxidized, it can't cause the reduction of sulfate. Okay, but what about if we test the other one? Okay, so now if we do that reaction, okay, so I'm running a little bit out of space here. See if I got enough to squish it in. So if we do that reaction, my reduction is, for the nitrate, is this guy. Okay, so plus 0.96. Okay, and then my oxidation, of course, we flipped it. Okay, so it's plus a negative 0.34. Okay, and that one comes out positive overall. Okay, so when I add that up, ESO would be positive. Okay, so copper can, by being oxidized, cause nitrate to be reduced. Copper cannot, by being oxidized, cause sulfate to be reduced. Okay, so in terms of the gold, I hope what you would say about that is what could gold cause? Okay, by gold being oxidized by going in this direction. Okay, by flipping the sign. Okay, by gold being oxidized. Okay, we would flip that sign. Make sure I got that right. Yep, 1.5. Gold does not want to be oxidized. Gold does not want to be oxidized at all. So by gold, if we change that to oxidation, that's a negative 1.5. By gold being oxidized, it would not be able to cause the reduction of either one. Okay, because a negative 1.5 and a positive 0.96, a negative 1.5 and a positive 0.17, either way you cut it, okay, negative 1.50 is not going to make a positive ESO with either one. Okay, so we would say for gold that it would not have enough potential to cause a reduction of either one. Okay, so there you go. So you guys, I would say, sorry, I didn't mean to take so long on this one, but this is a problem you guys are going to see. Okay, and if you guys want to ask some more questions about it, I can give you another example. I promise, a straightforward one. But nonetheless, Ms. Shire and I have both done tons of examples like this. In fact, if you want to refer to page 17, you'll see some more. So just give it a go. Okay. So I'm going to look to see if there's any questions about that one. Okay. Sorry, it took me a minute to get the question clarified. All right. I'm looking in the chat. You guys want to throw anything out? Okay. Always make a positive ESO and life is good. All right. What other questions do we have? Let's see. I'm looking in the chat. I'm not seeing any new questions. All right, let me look over some of my notes, make sure there wasn't any big things that we missed. Real quickly, someone did ask about, well, okay, two questions were asked. One of them was about concentration cells. So like on the quiz the other day, okay, we were able to have copper actually react with itself. Okay, and on the reactant side, you always have the higher molarity. Okay, and on the product side, so that would be my copper 2 plus going to copper, that's my reduction. And then always the, whoops. Hold on, I lost my screen. The lower molarity is always on the product side. So that's kind of how it's set up. Okay, and that's my oxidation. So what I would remember, you got your reduction, you got your oxidation. Okay, is we're going to force this reaction to occur. And I think the question somebody asked was about how the masses of the bars would change. Okay, so I'm going to put the lower molarity one over here. Okay, that's my 0.001 copper 2 plus. And then I'll put the higher molarity one over here. Okay, now in terms of how the electrons are going to move, okay, so basically I want this lower molarity to go up in concentration, and I want this higher molarity to go down in concentration. So to do that, this is going to have to be oxidation on this side, and some of the copper from this bar, so like pretend those are little copper atoms, are going to lose electrons, and then they're going to go into solution. Okay, so that's how we're going to raise that concentration, is copper atoms from the bar are going to lose electrons. They're going to cruise through the wire. Okay, and then they're going to add to the copper 2 plus in solution, and they're going to raise that molarity. So guess what? What that means is that this bar right here is going to lose mass. It's going to become lighter. okay, because copper atoms are losing electrons to make copper 2+ ions and are going into solution. And then guess what? On the other side, the exact opposite is going to occur. These electrons are going to stockpile, and copper 2+ from solution, we'll say those are copper 2+ ions, we're going to gain those 2 electrons and we're going to add copper atoms. Okay, so what that means is this guy is going to gain mass. Sorry. Okay, they're going to gain mass. And there you go. So that's kind of how that story goes. So I would say if you can figure out what side the oxidation is, then you're golden. You can usually figure out the rest there. Okay, and so this side would be the reduction side. And in general, the reduction side almost always gains mass because usually gaining electrons and plating some of the metal. Okay, so hopefully that helps on that one. Looking through the chat. What other questions do you guys have? I was looking through my notes. That's pretty important, making sure you can always detect what bars get heavier, what bars get lighter. I think that's about it, unless you guys have any other questions. I will. One thing we probably haven't talked about too much was, let's just say, I'm going to just give you guys kind of a weird half reaction, if you will. It involves the periodate ion. Okay, making I2. Okay, and this guy's reduction potential is 0.09 volts. Whoops, oh boy. Sorry, how about 1.09? That makes a little more sense. 1.09. Okay, and I'll just give you another half reaction. How about involving nickel? Gaining 2 electrons, nickel solid. And that guy is maybe -0.25. Pulled these right off the white sheet, okay? So first of all, I would ask you, okay, let's make a galvanic cell. Okay, so what would be E cell? So hopefully you guys could look and identify, oh, these are both reductions. So I'm gonna have to flip one. Okay, so you always want to keep the most favorable one. So I'm gonna keep the top one and then I'll flip the bottom one. Okay, so we'll turn this one into an oxidation. Then we'll flip the sign and then we'll flip that guy. Okay, so it looks something like that. All right, so now you get yourself a galvanic cell. I just want to remind you though that when you add these together, so then your E cells of course would add together. Okay, so 1.09 plus 0.25, E cell would be like 1.34, right? Hopefully I did that math right. Just let me remind you that when you add up these 2 half cells, you've got to make sure the electrons lost equal the electrons gained. So we'd have to multiply this one by 2. Okay, so 2 times 5 is 10 electrons. And we'd have to multiply this one by 5. Okay, so you guys could do that and you could add them up. Okay, but my whole point is, do you guys remember how to do cell notation? Okay, so if I added those up, okay, and I asked you to do cell notation, what would that look like? Remember, cell notation always goes from what's being oxidized to what's being reduced. Okay, so in that case, you'd have to start with the nickel. Okay, and you'd be nickel solid is going to nickel plus 2. Okay, and so that's my oxidation. Then you'd have your salt bridge. Okay, then you got to tell me what's being reduced. Okay, so what's being reduced is the IO3 minus. But the one thing I want to remind you about is this is aqueous. Guess what? This reduction can't take place if it doesn't have H plus as well. So you know what? That should be part of the cell notation. And there were some foul questions that had to do with that, but I just want to remind you that if you need H plus for a half reaction to occur, then you have the active player and then you list the H plus next. And then what does it get reduced to? Okay, and I'm going to say this is aqueous. So everything's in the same state of matter. Okay, so I'm just going to have it go to aqueous I2. Okay, and if it was solid, it was a phase change, then you'd use a vertical bar. But if it's all aqueous, 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 then you use a comma. And then since there's no solid in this half reaction at all, you'd have to provide a non-reactive conductive solid. So that's when you would do this vertical arrow to say you're changing states, and you could use platinum or you could use graphite, whatever you want. Okay, but you wouldn't want to forget that. Okay, so that would basically be the complete description of the reduction. Okay, so what's being oxidized first? Salt bridge, what's being reduced? If you have any important like conditions, okay, kind of add that in, and don't forget the non-reactive conductive salt. Okay, so that's something you guys can see. Okay, so quick question. Kavya said, even if there is an electrolytic cell where E cell will have to be negative, true, do we always want the most positive value from the reaction? Like, do we choose the value closest to 0? Kavya, I would say that's true. So for electrolytic cells, if you're picking reactions, you always, no matter what, you want to choose the most favorable possible half reaction. So if it's electrolytic, the most positive or the least negative. Okay. Yep, that looks good. All right. Other than that, let's see. You guys don't forget about how salt bridges work in general. Okay, I'm sure you guys maybe have studied that, but like the anion always goes to the anode side, the cation always goes to the cathode side. But if I asked you to explain why, you should always say for ion neutrality, you should talk about how you want the ion charges to be balanced out and not just charges. Okay, so make sure you talk about ion neutrality. Okay, not just neutrality, not just evening out the charges. Okay, so it's all about making sure the ion charges in the solution are balanced out. Okay, well, I think we're coming down to the end. Let's see. We talked about Le Chatelier's principle. Yeah, talked about electrolytic. We talked about galvanic. All right, what other questions do you guys have? All right, well, I appreciate you guys taking some of this sunny day to be with me. If you guys have any other questions, don't hesitate to reach out to your teacher and make sure and get a good night's rest. Okay, I think you guys will do great. I think the assessment is pretty straightforward. I'll stay on here for a minute. So if you have a quick question you want to talk to me about, go ahead. If you want to talk to me about anything individually. Oops.